Hello and welcome to Fast Talk, your source for the science of endurance performance. I'm your host, Trevor Connor, here with Coach Rob Pickles. Pick up any recent exercise physiology textbook, and there's going to be a very nicely drawn graphic showing how we use carbohydrates and fat for fuel, and an equally detailed graphic showing all the physiological attributes needed to perform as an endurance athlete. But there was a time when this information wasn't in the textbooks, simply because researchers still had to figure it all out. How important is VO₂max? Can we improve efficiency? And how much do we rely on fat for fuels? These were all questions that hadn't been fully answered when Dr. Edward Coyle began his career. But over several decades, he became one of the seminal researchers answering these questions. In this episode, Rob and I review 3 of Dr. Coyle's most well-known studies, including probably his most cited, which dives deep into how our muscles use the various sources of carbohydrates and fats for fuel. We all know that our muscles use a mix of fat and carbohydrates. But what's truly novel about this study is how our muscles balance using the fuels already in the muscle cells versus what's supplied in our blood. Dr. Coyle came up with a very novel way of solving this question. Next, we'll shift to a 1999 review where Dr. Coyle tries to take his decades of research and create a chart of all the factors that contribute to performance, including what he calls morphological components and functional abilities. In this study, you can see him thinking through all these factors in real time and ultimately coming up with a graphic that laid the groundwork for the beautiful summary graphics found in most exercise physiology textbooks. Finally, we dive into a 2005 study as perhaps Dr. Coyle's most famous and controversial, as it ended up at the center of probably the most famous doping scandal in professional cycling history. Dr. Coyle was able to collect data on a many-time winner of the Tour de France, from when he was a U23 rider until after his first win, and offer his assessment of how this rider became the best in the world. Both the quality and the ethics of his results have been challenged. Rob and I finished the episode diving into the science and controversy of this study. It's not one to miss. Also, one quick correction. We got our dates mixed up in discussing the final study. The study was published, and the controversy that was at the center of it occurred in 2005, not 1999. So, get ready for a little controversy, and let's make it fast. Well, Rob, we haven't done a seminal episode in a while, so good to get back to one. Love doing the research. We picked Dr. Coyle for this one, and you were just looking him up. So what do you have to say about his background?
1982, that's what I have to say. The year I was born was the year he started teaching at University of Texas in Austin, which makes him there for, 42 years old? 42 years.
Wait, you were born in 82?
Yeah, man.
You're younger than my brother.
Okay, good. I'm younger than a lot of people and older than some other ones. I don't know where to go with that. I want to talk about Dr. Coyle and not butts. Yeah, this guy has been around. He's been, supervising professor involved with a lot of really well-known researchers, meaning he's sort of trained the next crop of people that we're hearing from today. And, his research has been foundational for a lot of what we understand. And, oftentimes, though, it is funny, sometimes I look at the dates of these research studies, and today I think we have one from 93, one from 99, one from mid-2000s. Yeah. In some regard, it seems like so long ago, and in other regards, it seems like it really wasn't that long ago. And so we're making some pretty major discoveries and understanding of how the human body works, of how exercise improvement and adaptation occurs. And really, it was in the last 20 years, right, that we're learning some of this stuff. So pretty incredible, but really excited to talk about Dr. Coyle today. I think it's going to be a good one.
Yeah. So Dr. Coyle has pretty much spent his career at the University of Texas in Austin. And when you talk about kind of the meccas of exercise physiology, that is definitely one of them. You look at the names that have come out of there. Dr. Andy Coggan works with Dr. Coyle. Dr. Seiler went to school there. There's a lot of big names that came out of that university.
Sure is. And this isn't really the first time, well, maybe it is the first time we've talked about Dr. Coyle, but you talked with Dr. Coyle back on episode 146 when you discussed cardiac. 146.
That far back?
That feels like a long time ago, right? Yeah.
No, it felt like I just did that like a year or two ago, but I guess it was a while ago.
You guys, you talked about cardiovascular drift, and I wasn't a part of that episode, and so I'm going to go back and listen to it. I'm sure it's a good one.
Yeah. Well, we'll put the link in the show notes. So, yeah, going to your point about if you look at the dates and it looks like a long time ago, but in other ways it doesn't feel like that long ago. The thing I found really interesting is you buy an exercise physiology textbook nowadays, and like very basic exercise physiology is going to have all the, when you consume carbohydrates, here's the whole process, here's how they're used. When you're at intensity, you're using glycogen plus this much glucose. I mean, it's all figured out. Same thing for fats. You can read all very nicely laid out. Here's what happens with fats when you consume them. Here's what happens at different intensities. Dr. Coyle was doing some of his best research at the time when we didn't know all this.
Right.
And so you read this study and some of these studies, in some ways you go, well, I knew all that. But you have to remember at the time, they didn't know all
this. Yeah,
didn't
know all that back in 93.
You're basically reading the studies where they figured this out.
Mm-hmm.
And that kind of makes it fun. It kind of makes it neat to go back and read this.
Right. Yeah. So, Trevor, let's kick it off with this first one. And for full transparency, when we do for full transmorphication.
Yeah.
For full
Your coffee's right there. You might want to drink a little more of it.
It is. For full transparency. That's a word, right? Transparency. Holy.
There you go.
Wow. I honestly thought that transparency was a word for a moment.
I want to look it up. It sounds like it should be a word.
It should be.
I bet you it is.
That's I am so smart. SMRT. Sorry, Simpsons reference for you people born in 1982.
Keep going. I'm looking this up.
Okay. Trevor and I, we pick a researcher who has had great influence, and then we look back through their studies. We try to get maybe some research that represents different times of their career or different topics or whatever else. And in this one, I just want to say, Dr. Coyle wasn't necessarily the first or the last, the supervising author. He was the second author on this paper. And it was Dr. Roman, Romijn, that was the first author. But this was regulation of endogenous fat and carbohydrate metabolism in relation to exercise intensity and duration. Again, something that seems, I don't know, maybe it's not well understood now, right? But it feels like a really simple topic. But they really dived into it. And they dived into it, Trevor, by looking at the metabolism and by understanding a little bit deeper, not just using the indirect calorimetry that we normally use, right? That's when people collect breath by breath, oxygen and CO2 values. But they also use some tracers, some stable isotopes.
Yeah, and I think that's really important. By the way, before I go there, not a word.
Not a word.
But Transparity is a leader in Microsoft technologies.
Well, there you go.
So we can hire them.
I don't really like Microsoft or Microsoft products.
Yeah, well,
although I use OneNote. OneNote's great.
OneNote is great. That's where I keep everything. So I actually found it really interesting. I've seen this with some of these older studies where you have the elements that we all know and you see again and again and again the research. But there were some elements in this study that we've just kind of forgotten about. That
sure.
To me were some of the most interesting parts. And as you said, it was because they used the stable isotopes.
Yeah.
So when you do indirect telemetry, that's where you see somebody on the bike with the mask and they're measuring VO2 and VCO2, and they can figure out what's the ratio of fat to carbohydrates. We all know that with increasing intensity, your body uses more and more and more glucose for fuel and becomes more reliant on it. Where you have more of that parabola with fat, where up to moderate intensities, you're using more and more fat for fuel.
Hopefully.
And then, yes, hopefully. And then as intensity gets fairly high, you actually start using less fat for fuel and you're pretty much relying on glucose.
Right.
That's established, and we've known that about that for a while. But they wanted to get deeper into this. They wanted to say, look, you have plasma, your muscles can pull fat and glucose out of your blood, out of the plasma, but it also has intramuscular stores.
Mm-hmm.
You have glycogen, and you do actually have some stored fat in your muscle tissue. And so they wanted to see, how does that work? What's the balance between those? And either I saw that a long time ago when I was studying this in school
sure
and just forgot. Yeah. But reading it, I was like, man, I don't remember ever seeing this.
Right.
And it was kind of exciting.
Yeah. And so these tracer isotopes, if I remember right, it's kind of like, there are radioactive materials that break down over time. This is an isotope of, they used glycerol and palmitate that were stable. There's no radioactivity there, But because the molecule is different, they're able to measure it at the end and say, well, here's glycerol, but it's the labeled glycerol. So we know that it came from the infusion, and it can help them sort of back calculate exactly where we're pulling from and understand that metabolism a little bit deeper.
Right. Which is kind of neat. So, another example of that is you can label a glucose molecule. Actually, can you label a glucose molecule?
I'm sure that you can, but they did not use labeled glucose in this.
They did not.
They were able to look at blood glucose.
Yeah. But so, for example, you can label a glucose molecule and then put it into the body, and then you start measuring the outputs. So the end products of oxidative metabolism are your CO2 and water.
Yep.
And you can see, hey, was it fully oxidized by looking for those markers in the end products. Yep. So, one important thing to point out here, and this is a big part of the paper, they had to make a lot of assumptions. So they're using these stable isotopes, but then a lot of calculations are involved to try to figure out exactly how fuel is being used. So, they label the glycerol, but they have to make the assumption that all glycerol that they then measure in the blood comes from triglyceride breakdown.
Yeah.
So triglyceride is just 3 fatty acid molecules bound to a glycerol. So if you use those fatty acids to produce energy, you're just going to end up with a glycerol molecule that your body will then send back to the liver or adipose tissue and produce another triglyceride. So they had to make the assumption that all of that glycerol comes from the breakdown of triglycerides and that there's no breakdown of the actual glycerol molecules. Another assumption that they made was that all glucose was being used for fuel. And these are, they admit, big assumptions. And what they kind of say is, that's not 100% true, but there's not enough of these other weird things going on to be physiologically significant. But the question is, can you really say that?
Right.
So I think really there were a lot of things that they discovered in this study. So let's put those assumptions aside and let's say, for the most part, you can buy those assumptions. Based on those, there were a lot of interesting discoveries. But I think the biggest thing that they point out and where they start is that with glucose, it's fairly simple. Increasing intensity, you use more and more glucose for fuel. It's just that simple. Yep. It's not that simple with fatty acids, with fatty acid consumption. So they certainly saw you don't use much at low intensity. You use the most at kind of that moderate 65% intensity.
And just to put that into perspective, we're talking about sort of a base zone, 1.5, maybe 2 millimoles of lactate.
Yeah. So they have it. We should have mentioned this. There's 3 intensities that they use: 25% of VO₂max, 65%, and 85%.
Right.
So 65% is that solid zone 2-ish type ride, maybe high zone 1.
Yep.
25% is noodling. Like that's a slow walk.
It's not even active recovery. Yeah,
right.
Exactly.
85% is anaerobic threshold.
Maybe even higher. They said that the subjects could only maintain it for 30 minutes.
Right.
And they needed 20 minutes of steady state so that they could do their measurements. So that seems like it was like the highest workload they could get someone to do, which is important because they measured the 25% and the 65% VO₂max for both 30 minutes and 120 minutes. So they also looked at a duration time course, and obviously they weren't able to do that at 85% because literally nobody could ride that low.
Right. So, going back, glucose was simple. As you went up the intensities, you're using more and more. Barely touching it at the 25%, you're almost completely relying on fat. Fat, you saw the most usage of fat at the 65%, less at the 85%. But the other thing you saw with fatty acids is it gets a lot more complicated.
Yeah, Trevor, something that was interesting to me was that based on their glycerol, right, and you talked a little bit about some caveats there, but based on the glycerol, there appeared to be an increased call for free fatty acids that increased with each exercise intensity. So even though we have stated you're not using much fat at 85%, the body was still trying to liberate it through a process called lipolysis, right? The cutting of fat, lipolysis. So that lipolysis was potentially occurring but we weren't getting it perhaps into the bloodstream. And they came to that conclusion because in the 25% and the 65% VO₂max conditions, as soon as somebody stopped exercise, the rate of appearance of these free fatty acids in the blood decreased. Okay, exercise is done. We don't need much fat anymore to fuel that exercise. But in the 85%, as soon as somebody stopped exercise, there was a big flood of free fatty acid into the bloodstream. And they hypothesized that there might have been lipolysis that was occurring, but for some reason, the free fatty acids weren't able to get out of the adipocyte and into the bloodstream and to the working muscles.
Right. So it's a fascinating graph to look at. Like you look at the 85% intensity, you look at glucose usage.
Yep.
And it's just boring, straight line. But at the 85%, as you pointed out, in the first couple minutes, you actually see a drop in the available free fatty acids. And then at the end of the exercise, it just shoots way back up.
Yep.
And then slowly comes back down. And they also pointed out, as you said, that the lipolysis exceeded what was being used.
Yep.
So the body's trying to keep up, but it just looks like it can't get these free fatty acids to the working muscles. And, some of their explanations for that were, one, there's less blood flow to the adipose tissue because you're trying to get oxygen to the working muscles.
Correct.
Which is more important. The other issue is free fatty acids can't just be completely free in the blood or triglycerides. They need to be bound to something called albumin.
Yep.
And so there's a question of albumin availability. So basically what you're just seeing is our body's ability to get the fats to the working muscles just isn't that good.
Correct. And, hey, it might be worthwhile to put your body's effort somewhere else. Like you were pointing out, we don't need blood flow to the adipocyte. We need blood flow to the skin for cooling. We need to get oxygen to working muscles. And so even though, maybe it would be more efficient in some aspects to liberate those fatty acids, in the whole scheme of things, in the big picture, not beneficial.
Yep. It's the good old, we have enough blood in our system to do some things, just not to do all things.
Right.
And so you have the similar issue of when you're going really hard, blood flow to the gut shuts down because your body's assumption is if you're going that hard, you don't care about eating right now. You're probably trying to survive.
Yeah, it's interesting too, nowadays in 2024, all the rage is on multiple transportable carbohydrates, 90, 120 or more grams a minute. And in this study, they're still in that era of 30 to 60 grams a minute of carbohydrates.
Was it this study or the next study where he's talking about trying to get 40 to 60 grams of carbohydrates?
I think it was the next one that we're going to talk about. Yeah, but they do talk about that a little bit in this one. And Trevor, I think that we both thought some of the glucose changes were interesting. You want to dive into that?
Yeah. So he has a really good graph in here that I think summarizes so much of what they try to talk about. And like I said, this is where it gets interesting, is looking at the plasma sources of free fatty acids and glucose versus what's already in the muscle. So muscle source of glucose is glycogen, and you also have muscle triglycerides that you can break down. And what you see is at the low intensity, you are getting almost all of your energy from plasma sources. You're just not dipping into the muscle sources at all. The other thing you're seeing is primarily your fuel is just the free fatty acids that you're pulling out of the blood because you're just not going very hard. So there isn't a blood delivery issue. You can get what you need and it just gets supplied.
Yep.
As you get to 65%, what you start seeing is a greater reliance on the muscle sources of both glycogen and triglycerides.
Yep.
And that's where you see the greatest usage of the muscle triglycerides. And you're starting to see an increase in the plasma glucose usage. And then when you get to 85%, your biggest fuel source is glycogen, muscle source.
Two-thirds muscle glycogen.
Right.
Yeah. Yep.
Now, what's really interesting, so this is based on calories, is you look at total calories coming from combined plasma free fatty acids and glucose. It is the same across all three intensities. You're getting about 80 calories per kilogram.
Yeah, about that range. Yeah.
Yeah, kilograms per minute. Notice that's a small c, not the big K.
Yeah. And
Calories.
for what it's worth, the vertical axis on this is in increments of 100. So Trevor's guess of 80 is pretty close, I'd say.
Yeah. But it is exactly the same. So no matter how hard you're going, you're getting about the same amount of calories from blood sources.
Yep.
Now, at higher and higher intensities, it's more and more plasma and glucose than free fatty acids.
Yep.
But combined, they're about the same. So as you increase intensity, you're getting those extra calories from muscle stores.
Yep. Yeah, and I think that this is interesting because our ability to transport energy in the form of both glucose and free fatty acids is somewhat limited through the body. And this is a concept that we've brought up before, but if people haven't heard it, essentially carbohydrate, when it's stored in muscle, it's locked in the muscle. The carbohydrate in your thigh can't go to your tricep, doesn't work that way. But carbohydrate that's stored in the liver is able to actually leave the liver, hit the bloodstream, and go anywhere in the body that it's needed. But we're very limited in the amount of calories that we have in carbohydrate. It's going to say that it's around 400. It's going to vary a little bit depending on, the size of your body and how carbohydrate loaded you are. But that's only 400 calories. And we know you can cruise through 400 calories very quickly.
Yep.
So if plasma glucose was your biggest source, you'd be running out of fuel immediately. So it's almost like this dose-metered relationship that's occurring.
Yep. Now, I think the other interesting thing that they show, based on everything that we were just talking to you about, is at those high intensities, you're so reliant on what is inside your muscles.
Mm-hmm.
That store isn't very high. This is why you just can't do those sorts of intensities for very long. You're going to start depleting those energy stores.
Right.
And that's why they couldn't do the 2 hours at that sort of intensity. Because what you saw at 65% and 25% is they had them hold that for 2 hours because they wanted to see the effects over time.
Yep.
And what you saw over time was initially using a lot of the intramuscular stores.
Yep.
And then because they're depleting that, becoming more and more reliant on going back to the plasma source, becoming more reliant on that over time.
Correct.
But at that high intensity, you're going to deplete the intramuscular stores before you really have that option to replace that with the plasma stores.
Exactly, right. So to recap that, when we talk about the contribution at 25, 65, 85%, initially we're talking about kind of at the onset or 30 minutes into exercise is when they measure it, 30 minutes. But no matter what we say there, as exercise length duration increases, you run out of your stores in your muscle and you have to rely on plasma. Doesn't matter what intensity you're at, everything shifts to plasma over time.
Yep. So, believe it or not, as complex a study as this is, I think we kind of hit the main points. Is there anything else that you can think of that we need to discuss?
Oh boy, I'm sure there is.
I'm looking at my notes. I have a ton of notes in this study. I love the studies from back in this time where they would let them go 4,000 or 5,000 words and just go deep into this stuff.
Yeah. Duration did not have much of an effect at 25%.
That's true.
But it did at 65%. So when you're out there and you're not really doing anything, like literally like meandering around the block, we don't necessarily see the shifts that we talked about. But I will say, Trevor, I think that everything you just said holds true because the vast majority of people are going to be working at that 65% and, or higher. And so I do think that relationship with duration holds true. So
yeah, and I just want to emphasize how slow 25% is. Like this had to be done on a trainer because they sent you out on the road and said, stay at 25% VO2 max, you might fall over.
I'm pretty sure it was on a Monarch bicycle pedaling at 80 RPM.
Yep. So, to me, the key message with this study, and this is one of the most referenced studies that Dr. Coyle's been part of, is this is at the time when I shouldn't say I was a kid. I
was 11.
Yeah, there you go.
93. Yeah, I was 11.
Yep. They were still figuring all this out. Like this was pretty groundbreaking stuff of figuring out how does our body use carbohydrates and fats at these different intensities. How are we using plasma versus intramuscular stores? this would have been a very, very exciting study at the time.
Yeah. You know, Trevor, if we move on to the next one, which was a measly 6 years later, I'd say that this paper that Dr. Coyle wrote, he wrote this by himself, 99. It was in the Journal of Science and Medicine and Sport. I think he has a lot of things figured out at this point, you know, where this paper titled Physiological Determinants of Endurance Exercise Performance is the culmination of a lot of these other earlier research studies that he's done. And now he's attempting to put together a model of endurance sports performance. And this is definitely one I'm going to encourage everyone. Check out the show notes, head over to fasttalklabs.com. You have to see the visual, the chart that he has in here, because that chart is the entire reason that I propose this paper be part of the episode.
Great chart.
Exactly, because, you know, and we'll talk more in depth here, but this chart ultimately lays out, hey, performance velocity is here, right? How fast you're traveling over ground, how fast you're riding your bike. These are all of the things that play into it. Resistance to movement, your lactate threshold power, what plays into that? Oh, your stroke volume plays into that. And it's this big, large visual model. And for me, it emphasizes the fact that we oftentimes spend so much time on the minutia, right? Yep. You know, we're talking about PPAR and, you know, everything else, all of these agonists. And sometimes we need to step back from the minutia and we need to look at the big picture and say, how does all of this stuff fit together? Why do we even care about muscle capillary density? Right? Yep. Why do we care about mitochondrial density? All we do is talk about how do we improve mitochondrial density, but so what? What does that affect? This paper lays out that big picture of how interconnected all of these measures and morphological considerations are.
Yep. What I was surprised about by this review was how short it was.
I know.
It was a very short review, but as you said, the visual told a lot.
All you need is figure 2. It could have just been the figure 2 and no words.
But you can really see in it that this is him taking probably a decade and a half of research that he had done before that. And it's him trying to pull it all together into what does this mean?
Yep.
And so you even see, in some ways, I thought it was written as obviously he probably went back through it multiple times. But you can see very much that it's him figuring things out, how to pull all this together and what are all the key pieces. It actually reminded me, we just did an episode with Dr. Seiler, who did a review talking about everything that he's learned about high-intensity interval training. And you saw in his paper a lot of the thought process. You saw him go on these tangents, like breathing rate, and then coming back to the main topic. And there was a bit of that here where he starts the paper by talking about, you know, the 2 biggest things that impact you are heat and acidosis. And then, you know, starts to talk about those, but then goes, let's talk about all the things that affect your performance or factors in your performance. And then at the end comes back to heat and acidosis and all that.
Yeah.
So it's kind of start here, but no, now we need to talk about this. And then let's go back with the context.
Yeah. I will say, you know, my biggest caveat with this paper is I think that this is very applicable to laboratory-based endurance performance, meaning if you're measuring endurance performance in more of a steady state effort, a time trial, a time to exhaustion, out on the road, maybe that's more of like your marathon and your 10K where you're leaving the starting line, you're trying to run your best time and cross the finish line. I don't know that this model explains all the variance when we say, maybe talk about crit racing or road racing on the bike, where it's a little bit more heads up, it's a little bit more strategy, it's a little bit more attacking and recovering. Then I think that this model is still probably explains a lot of endurance performance, but I do think that it leaves some things out.
Yeah. I mean, he touches on, but doesn't really get into the neuromuscular side.
Correct. Yeah.
You know, a lot of those other things. Another thing, I always have to point this out. You can tell it was written in the 90s because he talked about lactic acid.
Yeah, there is lactic acid.
Literally, it's in one of the diagrams.
Yeah. Well, at the very least, we know that there is a hydrogen ion associated with the release of lactate from the cell.
Yep. But that figure 2 that you talked about, This goes back to what we were saying at the beginning of this episode, that there's some studies that go back and go, well, I already knew all that.
Mm-hmm.
But you have to remember at the time, this was groundbreaking.
Yeah.
And that diagram, every exercise physiology textbook has some version of this diagram.
Yep.
But you have to understand that this is one of the key researchers who figured this diagram out.
Right. And there have been other researchers that have taken this diagram in the subsequent years and expanded upon what it means. So, if we sort of describe this diagram a little bit, close your eyes, visualize this for the people who are able to, at the very top is performance velocity, meaning the speed that you're holding for whatever the event is or the duration that you have to.
So he defines performance as the speed at which you can do a certain amount of work.
Okay, is that what it was in here?
Let me read it.
Yeah.
Performance can be evaluated by the amount of time required to complete a given amount of work, i.e. power.
There you go.
Or by the length of time that a given power output can be maintained, i.e. capacity.
There you go. Playing into that performance velocity, he has resistance to movement, and that is a whole show on itself, right? That's aerodynamics, rolling resistance. We're cyclists, so we'll think about it this way, the resistance in your bearings and your drivetrain. He doesn't go into that. But the other thing that's playing into this performance velocity is your performance power. Okay, great. That makes sense. As my power goes up, my speed will probably go up too. But playing into performance power is two things that are really important. The VO2, the amount of oxygen that you're consuming, and your economy of movement, how much work you're getting out of that oxygen. Those are the two biggest things that are playing into the workload that you're able to sustain in your performance.
Yep. So continuing down that chart, so I'm actually going to take a step back, and I will tell you, I half reread an older paper of his before I realized I was reading the wrong paper. It was one of the three that we picked.
Oh, okay.
But there was a paper he wrote in '88 called Determinants of Endurance in Well-Trained Cyclists. And there's several other researchers who did very similar studies. There's another one by Michael Joyner. Actually, here's another one, Michael Joyner and Edward Coyle.
Yep.
I always remember it as the Joyner paper. Endurance Exercise Performance, the Physiology of Champions.
Yep.
So this is some of his, that one's actually 2008.
That one's later.
Newer. Newer. We're
Wow.
both having problems with the word today. But both of those studies talk about three key factors in performance, which is your VO₂max, your lactate threshold, and your efficiency/economy.
Mm-hmm.
And saying those really are what separate a top endurance athlete from the rest of population. Those kind of key three things. And if you look at this chart that you just described the top of, you go down, there's a dotted line below what you just talked about, and then they talk about the functional abilities, and that's where you have your maximal oxygen consumption, your lactate threshold, and your economy efficiency.
Mm-hmm.
So it's those three key things. And that's one of the things you've really seen with Dr. Coyle is he has hammered on those again and again and again in his research.
Right. Yeah, I think that 1988 paper is awesome, the determinants of endurance in well-trained cyclists, but it doesn't have the figure 2 chart.
No, it doesn't.
It doesn't.
Because it's way earlier. It's 11 years later that he puts all this together.
Yeah, and that's more of a research-driven, like, we're going to figure this out in cyclists, and this later one that we're talking about is more of like, okay, what's the model? How does this stuff fit together?
Yep. And part of the reason I just brought those three things up and the importance of those is because I'm giving a little teaser to the final Dr. Coyle study, which we're going to talk to. You've seen in his research, he's been very interested in economy and efficiency.
Yep.
And in that third paper, when we get to it, it kind of bites him in the butt a little bit.
Yeah. So let's talk about that economy and efficiency a little bit. So in this chart, he has the performance stuff on top. In the middle category, it's labeled functional abilities. And then at the very bottom is a row of morphological components, right? This is factors within your body, your capillary density, your stroke volume. The thing that plays into the economy of movement the most is going to be your muscle fiber type.
Composition.
Right? And type 1 fiber composition explains, based on the numbers that he has here, 56% of the variance in economy. So that alone explains over half. And it's disheartening for somebody like myself, who's probably more type 2 dominant, sitting across the table from Trevor, who's probably more type 1 dominant, and just say, God damn it, I will never be as economical as Trevor is.
Yep. Sorry.
But there's, you look at this chart, and it's percent of type 1 muscle fibers and gross efficiency when cycling, R value of 0.75, very, positive relationship between the two. It's pretty incredible how they found that alone. Okay, so what does that mean for us? If two people are riding at, say, the same oxygen consumption, two people going down the road at 3 liters of oxygen per minute, the one that's more economical is getting more watts from it.
Yep. And by the way, notice I haven't corrected you at all about efficiency versus economy.
Well, he uses both in terms of mechanical efficiency and economy of movement, which would be watts per liter.
Yep. And I'm just going to give another teaser. I said in a previous episode when you and I started arguing about the definition of efficiency and economy, that we had done an episode on it.
You hadn't?
We hadn't.
Yeah. See?
I had written an article on it. I had written an article. We never did an episode.
Can't trust them. Can't trust them.
We're doing that episode.
Can't trust them.
Rob and I are going to have it out.
We're
going to debate it.
Well, my type 2 fibers are going to out headlock your type 1 fibers. So.
And I will say that when we have that debate, we're going to be referencing Dr. Coyle studies a lot because he was big on this.
There you go.
But, I love evolutionary biology. There is a rational reason or a good reason for this. Our type 1 fibers are what you're doing when you're doing more endurance type activity. You look back at our ancestors, they would run for a long time, but they didn't run fast. They weren't trying to win a marathon. So it was kind of walk running. So those fibers didn't need to be strong. They just need to be efficient so you could go for a long time. Type 2 fibers, particularly your 2As, are your really strong fibers. That's when, if you're a hunter, you're going in for the kill or you're trying to lift something really heavy. You just need to be powerful when you're using those fibers. You don't need to be efficient. You're not trying to do that for a long time.
Right. And when you talk about efficiency, I think it's important, and he mentions it in here, and I want to point it out to people. The gross mechanical efficiency that they saw in cyclists was between 18 and 22%.
Right.
And that is significantly less efficient. Most people assume 25%. And assuming 25%
in that past episode,
is
and you jumped all over me.
So much higher than we actually see in people. We produce a lot of heat. Right? That's where all of the extra energy is going for the most part. Let's be honest, right? We're only getting 18 to 22% of the energy that we're burning is actually powering our legs going to the bike. And I'm tying that. You'll see how all of this comes full circle. The other thing that we adapted really and evolved with is our ability to manage heat much better than those things that we were chasing down over time, right? My dog pants out his mouth. His long, 2-foot long tongue is dragging on the ground because he can't sweat, can't do anything else. But we have done a great job of heat. And that is something that interestingly is only somewhat touched upon in this paper.
Yeah. So some researchers have said humans are the purest endurance animals on the planet for a couple reasons. One is we actually don't have the type 2A fibers. We have 2X. All of our muscle fibers are able to work at least somewhat aerobically, where a lot of animals have the 2As, which can't do any aerobic work. So all of our fibers can work aerobically. But another reason is our skin is porous. We are much better at dissipating heat than a lot of other animals. As you said, your dog, only way it can get rid of heat is by panting. Horses can sweat, but they're still not great at dissipating heat. So while they can kick our butts in a 10-mile race, they hit a certain point where they overheat and they have to stop. So they've actually tested this, put a good endurance runner up against a horse in a 100-mile race. And a human can give a horse a run for its money in a 100-mile race.
But I don't think the horse cares about money, Trevor.
Yeah, that's fair. Horse doesn't have a lot of money, so it's not much of a bet.
Run for its oats. The horse is worth a lot of money, so I guess there's that. No, you're entirely correct. And on this heat side of things, I just want to say, I think that they do point out that pre-cooling, better performance, preheating, worse performance. You don't hear about preheating very often, but this is an area that I don't think that athletes emphasize enough. And a quick story, my daughter runs track. Very hot day over the summer. She was running like USATF regionals here in Colorado. So I went to the Kona Ice, the slushy truck, was parked outside, got her a slushy, was like, here you go, sweetheart. This is going to help you run faster. Yeah. And she was like, I don't know, Dad. And she was like embarrassed to eat it, But this is like a number one thing, pre-cooling with things like slushies. But athletes almost seem like they're avoiding improving their performance in the heat. Another case is that oftentimes people will train when it's cool out. Like, oh, I'm going to go ride at 6 o'clock in the morning because it's cool out. Even though the race they have coming up is going to send them exactly through the heat of the day. And so I think that people ought to be spending more time focusing on this thermoregulation because it can really improve your performance. At the very least, it's going to improve your plasma volume, which improves stroke volume, cardiac output, improves your lactate threshold, improves your VO₂max. Even if it doesn't make you feel more comfortable, which it does in the heat, you get actually performance exercise benefit from it just because of the adaptation to the heat itself.
Yep. No, I agree.
Sorry, that was a rant. Was that ranty?
No, that was good.
Oh, okay, good.
The thing I actually want to go back to, because I just want to give you credit for this. When you said people think we're 25% efficient, and that's not the case. It sounds like we're splitting hairs here, but here's how important it is. If you're 25% efficient, unless you have the worst VO₂max in the world, go race the Tour de France because you have a good chance of winning it.
Yeah.
The difference between 21% and 25% is, decent racer versus Tour de France champion.
Yeah, Trevor, to put that into perspective, they had subjects with the same performance VO2, and this is just looking at the high percent type 1 versus like the normal percent type 1. And it was 342 versus 315 watts were the difference in the two of those. A 30-watt difference just based on sort of the economy of people.
Yep.
That's crazy.
Yep. So I think the last part that we want to talk about with the chart, we have his three key things, which he has hammered on again and again and again: VO₂max, lactate threshold, efficiency/economy.
Yep.
But then the bottom of the chart is the physiological, or what he calls morphological components,
right,
that determine whether you have a good VO₂max, whether you have a good lactate threshold, whether you have good efficiency.
Yep.
And we touched on one: muscle fiber type composition.
Yep.
More type 1, the more efficient you are. That's the only one that connects to efficiency. His others are capillary density, which improves your ability to both deliver oxygen and clear lactate.
Which was really interesting to me. That's something I don't think about all the time. I can keep going if you want.
Please. Please, you got me intrigued.
Yeah, well, no, just with the clearance of the lactate, right? They talked about like the diffusion distance and being able to get that lactate out of the cell by having the capillaries closer. Whenever I just think about muscle capillary density, I always think about the delivery and not the removal.
Yep. No, it's important for both. The next one in the list, which also improves oxygen consumption, is hemoglobin concentration.
Right.
And if you want to know how important that is, when you hear about all these athletes doping with EPO, they're just trying to increase their hemoglobin concentration.
Sure are. Or doping with carbon monoxide.
Yep.
The newest. Because xenon gas was apparently too hard and expensive to get, so they just went
carbon dioxide. Yeah.
Monoxide.
Okay, let's poison ourselves.
Ooh, no. Yeah, well, just poison yourself a little bit.
Okay.
Not a lot of it.
Good. Things people will do. Just kills me. Next one is stroke volume. Again, improves oxygen delivery because you're pumping more blood per beat of the heart.
Yep.
Aerobic enzyme activity. So now you're getting into the mitochondria, which is where aerobic metabolism happens.
Yep.
And basically, the more mitochondrial density you have, the more enzymatic activity you have, the better ability you have to take that oxygen out of the blood and use it to produce energy.
Correct.
And then the last one is distribution of power output and technique. So that gets a little into that neuromuscular side.
Yeah, the distribution of power output one was interesting as well because he talked about distributing the force that you're creating over a larger muscle area.
Yeah.
And in some regard, this was backward from how I always thought about it, in that more muscle, more oxygen for a given workload, potentially bad, right? That means you're less economical. You're using more oxygen to produce the same amount of power. However, I think that he's discussing this in sort of the vein of, okay, we can increase the mitochondrial density of a fiber, but we can also increase the fibers with high mitochondrial density. And by doing that, that's the increase of the distribution, not necessarily, say, calling upon type 2 fibers to do the work, having more type 1 fibers with great mitochondria to share the workload.
I think this is why we were both struggling with it, because normally when we think of an increase in muscle fiber, so you talk about the cross-sectional area of the muscle.
Yeah.
If that's larger, it's generally because you have more type 2 muscle fiber. You're just one of those big bulky guys who's really strong. Those fibers aren't as efficient. They can't really use oxygen, so that actually hurts you.
Yeah.
But you're right. If you increase the number of slow twitch muscle fibers, the cross-sectional area of that, you're going to be stronger on the pedal stroke.
Yeah.
So, yeah, I agree. I might get us in trouble, but I will put this chart in the show notes. It's a great chart, and please just understand. You're going to look at this and go, well, yeah, I've seen that in my exercise physiology textbooks. But again, this was the OG. He was one of the people originally creating this whole concept.
Yeah. You know, some last caveats on this one. He does call out, hey, this stuff only occurs this way in this model if the athlete is well fed, they're well hydrated, they're motivated, and they're not hyperthermic. And that any of those 4 things, and maybe more, could really undermine this model, right? You run out of carbohydrate, the rest of this probably, goes cattywampus a little bit fast.
Good point. Yeah, no, he does talk about the areas of fatigue. So I think we need to leave some time for the big study.
the big study. I think this is the elephant in the room.
Yes, it is. Now, I'm going to start by saying it might not be the case anymore, but certainly when I was doing my master's, this was like, if you were an exercise physiology student, you've read this study probably multiple times in different classes.
Yeah.
It was just the study everybody talked about.
Mm-hmm.
And so there is a lot of backstory behind this. So maybe we'll talk about the study, but then we're going to give you the whole story outside of the study.
Do we want to start with the title, or do we want to skip the title?
Go right ahead. Well, what I found really funny about the story is he's trying to be a proper researcher and not say who he's researching. But you're 2 sentences into, like, frankly, in the title, you can figure out who he's talking about.
Did you look at the references and look at what the first reference was?
Yeah, it was his book.
I was like, wow, that's a dead giveaway right there.
So a lot of researchers will study famous endurance athletes or famous athletes, but I guess propriety dictates that you try to keep it anonymous. This one, not so much.
Yeah, Trevor, I think that there's some researchers who have almost kind of made a career or a foundation of their career, like Dr. Lucia, who have studied elite athletes, but oftentimes I think that it's a group of elite athletes. And this particular paper that we're talking about, it's a case study of one particularly elite Tour de France multiple-time champion.
Yep. I'll give you another quick example before we dive into this. There was a great study by Dr. Pinot called A 6-Year Monitoring Case Studying a Top 10 Cycling Grand Tour Finisher.
Mm-hmm.
And when I read it, I went, oh, absolutely, that's Quintana.
Interesting.
I was wrong.
Really?
I was wrong.
Who was it?
I'm actually forgetting who it is now.
Thibaut Pinot? No.
Yeah. That would be interesting.
That would be funny.
It wasn't, but it was a French rider.
Uh-huh.
I'm blanking on the name.
Uh-huh.
But like I'm looking at my notes on it and I just used Quintana's name and then later found out, no, I had that wrong. So some researchers actually do this. They'll do the case study of a top athlete and hide it well enough that you don't know who they're talking about.
Sure. Yeah. Okay.
Not this one.
Let's talk about this athlete, Trevor.
Yes.
He got better over the years.
Yep. He was, at the time of the writing of this study, a 5-time champion or 6-time champion of the Tour de France.
At the time of the writing of this study.
Yes.
May or may not hold true today.
Does not hold true today.
Maybe he won more since this study came out.
Maybe he had them all taken away from him. If you haven't figured out who we're talking about.
The first reference is a book titled It's Not About the Bike
by Lance Armstrong. Yeah, so not well hidden. But yeah, I mean, it was fascinating that let's give credit where credit is due, and I don't think this was given by people that attacked the study. He started this research when Lance Armstrong was still basically U23.
Yeah, he was like 18 or something.
Yeah.
Right? Was it that young?
Pretty young. And just
21.
Just appearing on the scene. They had no idea when they started the study that he was going to be a multiple champion of the Tour de France.
Right.
That's important to point out. This was just a strong American cyclist. Remember, Dr. Coyle is down in Texas. Armstrong was from Texas. There's a certain rationale behind, let's study this guy. He's young. He has a lot of potential. Let's see if we can see what happens over his career.
Right.
It was just kind of that, oh my God, we just now got all the data for a multiple-time Tour de France champion.
Yep.
So I'm not sure we need to go into the minutia. I think really we just need to cover the overall results, which was, they did tests on him. So they did a lactate test. They did a VO₂max test. They measured gross mechanical efficiency and delta efficiency, which we'll talk about in a second. And they did this when he was 21. So I'm looking at the ages here, 21.1. And it looks like 21.4, so relatively close to one another. When he was 22, then there was a big gap because he had cancer.
Yep.
Then when he was 25.9, and I don't know why I'm giving the decimals, when he was 28. I'm just reading off here.
Very precise with ages.
Yes. Notice, so 28, that was November of 1999. That was the only one that was done after he had won any of the Tour de France titles.
And it was preseason, right? And they do call out training stage when he was 21 preseason, another preseason when he was 21, a racing season when he was 22. Like you said, the reduced training at age 26 because that was after the chemo and the cancer treatment. And then again, preseason at 28.
Yeah. None of these were done in season. None of these were done right around when he was on peak form. That's
correct.
Important.
The racing one when he was 22 was in September. So that would have been the very tail end of any racing that was happening.
So he ended up with all this great data on suddenly one of the greatest tour riders of all time at the time. And, obviously you want to dive into this and go, okay, in 1992, this guy was not capable of winning the Tour de France. This guy wasn't capable of a top 10.
Yeah.
Now he's a champion. Let's try to see what the difference is. And look, I'll state here the obvious. We now all know that he doped.
Yep.
We all know that was a factor. At the time, and we're actually going to get into this, he was fighting pretty hard against any claims that he was doping and saying he was doing this clean.
Yeah.
He had not admitted to it yet. So what they found in the study, there's a lot of things. There's a great chart in here that shows all the different metrics. But the key findings were VO₂max did not change.
It did not change overall. It did fluctuate a little bit up or down preseason to race season.
Yep. But overall, you didn't see a giant jump in VO₂max.
Yeah, to put that into perspective, right? January 93, a preseason VO₂max test, 5.8 liters. A preseason in 1999, 6 years later, 5.7 liters.
Yep. And now here's another thing that actually really makes you scratch your head. His lactate threshold as a percent of his VO₂max went down.
Correct.
And you look at any studies looking at top cyclists, top endurance athletes, and one of the biggest adaptations you see is their lactate threshold gets closer and closer to their VO₂max. It becomes a higher percentage, not a lower. He went from 85% down to 76%.
And was very stable at those, right?
Yeah.
And he dropped from 85% in November of 92 to 78% in January of 93. And then he stayed 78, 76, 76 for the remaining measurements. Yep. I have that highlighted on mine because I found that really fascinating as well.
And it's confusing. And note, they didn't measure that in 1999. Correct. So we don't know what percentage it was when he was winning the Tour de France.
Yep. So if we look at that as a percent, it drops, right? If we look at that in terms of lactate threshold O2 uptake in liters per minute, it drops even more. But because his VO₂max isn't necessarily going up either, that's why the percents, like his VO₂max is coming down, but the percents are staying the same because of that.
Yep. So what they found was there were only two things that consistently changed in Lance Armstrong. One was an increase in both his gross and delta efficiency, very similar increases, so I'll just give the gross. Went from 21.18% up to 23.05%.
Not 25.
Not 25. 23 is extremely high.
Yeah.
And an 8% drop in body weight?
Something like that. Yeah, his body weight, body kilogram was 79 essentially for that first measurement. Actually, race season, he was down to 75. He was back. He looks like he's about 79% when he's not in race season. But he does lose like 4 kilo from pre to race season.
Yeah. And what this amounted to was a net 18% improvement in the power that he could put out at a given oxygen consumption per kilogram.
Right. And so, we just talked about how this mechanical efficiency is what they're dubbing it in here. But when we look at power per liter, then we're talking about economy at 5 liters of oxygen, which is quite a bit of oxygen. Most people don't have a VO₂max.
Do that.
Exactly. At 5 liters of oxygen, initially in 1992, the very first measurement, he was putting out 374 watts at that point. Mm-hmm. That was 21% efficiency. A 2% increase in efficiency from 21 to 23. The very last measurement, 28 years old, 23% efficient. We go from 374 watts to 404 watts. 30-watt improvement for a 2% gain in efficiency.
Right.
That's incredible.
Yeah. And so the explanation here is that's what took him from an impressive cyclist to the dominant person that people remember.
Right. This is interesting to me for another reason.
Mm-hmm.
We assume these results are tainted because of the doping. However, the second to last measurement was at 26 years old. It was when he was just starting to ride a bike again. And it's as described. Believe this if you want or not. As described, it basically says like Lance hadn't ridden in months prior after his treatment, but he did ride for about a week prior to coming into this measurement, right? And I think that that's based sort of on Lance's recollection in his book or whatever else. Yep. One would assume in that case, he was not on any sort of doping products, right? That measurement after that was still 22.6% efficiency. It wasn't as good as his best, but it was much better than his earlier years. He was still doing 399 watts at 5 liters. So I wonder, I have to just ask, is the increase in muscular efficiency, which is literally the title of this paper, is that still valid, even though there are the doping sort of confounding factor here?
Well, that is the key question. And I think you're shifting us to the broader conversation about this study. And yeah, I'm going to start by saying I agree with you. We now know that Armstrong was doping. Mm-hmm. Doping will enhance VO₂max. It enhances oxygen delivery. It does not help efficiency. So, there is an argument that the weird things we're seeing in the lactate threshold and the not seeing no change in his VO₂max is because, like you said, they don't generally dope in the off season. You're constantly being tested. You're only going to take the risk when you really need to take the risk. And you don't need to be taking the risk in November.
Yeah.
So that's going to skew some of the results. And that's why it would have been great to get some results from him in June or July, Because I think you would have seen very different VO2 max and lactate threshold numbers.
Yeah, no, certainly, right. And his VO2 max at that time, where he was presumably off everything, 5.3 liters. The one measurement they have 3 years prior at the end of the race season was 6.1. And we can probably assume at its peak it was higher than 6.1, maybe a little artificially inflated with that increased hemoglobin like we talked about in the previous paper.
Yep. But now let's get into the dark side of this paper, because he published it and then it got challenged, because it's generally assumed, and we can talk about this too, but certainly at the time, the very strong belief in the science community is efficiency cannot be improved.
Mm-hmm.
We just talked about this in the previous paper. Really, efficiency is about the percentage of type 1 muscle fibers. And he talks about this in the Armstrong paper. And the belief at the time was fibers don't convert.
Yep.
You have what you have. You have the percentage of type 1 fibers you've got, and it's never going to change. And Coyle's explanation in this Armstrong paper was that Armstrong saw a substantial switching of fibers from type 2 to type 1. His percentage of type 1 fibers went up substantially. And they can't prove this because the only way to do that would be with muscle biopsies, and Armstrong wasn't willing to do biopsies.
Correct. Yep.
So it's a guess, and that was the conclusion of his paper. So it got challenged when it came out. A lot of scientists had issues with this, but then it got a little darker because at the time, I forget do you remember the name of the insurance company? There was an insurance company that was suing Armstrong. So Armstrong, or I guess U.S. Postal, was using this insurance company, and there was an agreement that if Armstrong won his 5th tour, they would pay him $4 million.
Sure.
And they didn't want to pay the $4 million. So they sued on the basis that they believed that what Armstrong did was not possible.
Yeah.
And that he was doped, and that negated the contract. So they didn't need to pay him, and they took him to court. Armstrong, so that was in 1999 that this court case was happening. This paper was published in 1999. And Dr. Coyle was paid by Armstrong's legal team.
Huh, I didn't know any of this.
To come and testify.
What?
And this paper was the center of it. And he said that Armstrong couldn't have been doping because doping doesn't affect efficiency. And what doping does affect, which is your VO2 max, your oxygen delivery, your lactate threshold, we didn't see improvements in that.
I never knew any of that, Trevor.
Gets a little muddy, doesn't it?
Well, it certainly does.
So that set a lot of researchers really off. And they then started to say, they claimed basically, it's one thing to make mistakes in research. It's another thing to have unethical practice in research. And a group of researchers basically called unethical practice in this and said they sued the university to get the raw data to see if there were any issues in how this was analyzed. And to this day, Coyle only released the results from the first test in, 1992?
Yeah, sounds about right.
He only released that first test. And so a lot of researchers are very upset about that, saying, if you're not trying to hide something, why wouldn't you release all of the data?
Sure.
They then did go into that data from the first test and discovered a flaw in the research.
What? You got to let me know this stuff ahead of time so I can be prepared.
Sorry, I only read all this last night.
What, no more midnight text from you, Trevor? It's like you don't even love me anymore.
Sorry about that, Rob. So, Rob, here.
Elucidate, Trevor. I need to know more.
So before I can elucidate, I'm going to throw this back to you, because this I know you understand better than me. Explain the difference between gross efficiency and delta efficiency.
Yeah, it's a great question. Gross efficiency, we're basically looking at what energy does it take to produce a certain amount of energy, right? And this is why it's an efficiency, and it's why it's a percent. Basically, this much energy nets you this much energy.
So it's energy used to energy out.
Exactly. Now, one of the major contributions to that is just the energy that it takes to, say, move your body through the range of motion, right?
Mhm.
Why that's important is this. If you sit on a bike and it doesn't have a chain on it, and you just start pedaling against no resistance at all, guess what? Your oxygen cost goes up, right?
You're
The amount of
expending energy.
Exactly, you're expending energy. So the movement itself takes energy. That has a larger contribution to low-level efforts, right? As a percent of how much it takes to pedal 25 watts, that's a pretty big percent. As a percent of how much it takes to pedal 250 watts, it's relatively less. Delta efficiency looks to remove that energy it just takes to do the movement out of the equation, so that we're looking more purely at how much energy does it take to actually apply power in the movement that you're doing. And that very simply is the slope of the line when you graph out more than one point across a graph. So we can make a graph of like gross economy, but we can also make a graph of the delta efficiency, and that removes that little bit of movement economy, I'll say, that gets put in there. For all intents and purposes, I think that we can just rely on the gross efficiency, and that's going to get us 99% of the way there.
So that is interesting, because here's the thing. So I just want to emphasize this. This is really important. So gross efficiency is factoring in all energy that your body's using. So even when
Correct.
you're sitting on the couch,
Yes.
you are burning energy.
Yes.
That's factored into the gross efficiency. So you're measuring how much energy your body is burning, your muscles, all your cells are burning.
Yep.
And then you're comparing that to how much is going into the bike and saying that's your gross efficiency.
Right.
But not all of that energy is being used for the bike. So delta efficiency looks at changes as you increase intensity. So that allows you to eliminate energy that you would just be using anyway if you were standing still. As you said, if you're just pedaling the bike with no chain,
Correct.
it eliminates that. So now you're looking at what is going into the bike.
Mm-hmm.
And when they looked at the delta efficiency, how he calculated it, what they discovered is, so delta efficiency uses that line. As you increase work rate, you see oxygen consumption going up, and you're looking at the slope of that line.
Yep.
But if you take that line down to where work rate is zero,
Yep.
oxygen use is not going to be zero.
Yep.
Because you're not dead. You're still breathing. The way he calculated it, the line goes to zero.
Correct. But that's delta efficiency.
No, but delta efficiency shouldn't go to zero.
It should.
No. When you get work rate goes to zero, you are still consuming oxygen.
Correct.
You're still going to have some oxygen consumption. What Coyle did, the way he calculated it, is when work rate goes to zero, oxygen consumption goes to zero. That's how he did the slope of the line. And when you correct for that, taking just those first results, and you have the correct delta efficiency line where it doesn't go, where you don't have zero oxygen consumption at zero work rate, and recalculate his efficiency in 1999, or when he was 21,
Mm-hmm.
it was still 23%. It eliminates
The improvement.
the improvement by
Interesting.
delta efficiency.
Hmm.
Coyle has argued against this and said, yes, I made that mistake in the calculation, but it's a minor factor and it doesn't impact anything.
Well, I think that it still leaves the improvement in his gross efficiency as well, which is a very simple calculation. Right. And we do see, changes over the years in that gross efficiency.
Yep. So here's where we're at with this. Dr. Coyle has still refused to release all of the data. When he's been asked about it since, he's gotten quite angry. And basically his statement is, don't these people have jobs? Don't they have better things to do? He's admitted that he made the mistake in the calculation, but has said it wasn't that important. It doesn't make that big a factor. And said ultimately what he was trying to do was take some very interesting data and try to explain something. He was not being paid to fabricate anything. And he still believes, there was an improvement in efficiency. I am going to point out, since then, there has been a little more openness in the science that, there is improvement in efficiency. So I'm actually looking at a 2019 study seasonal changes in gross efficiency and aerobic capacity in well-trained road cyclists.
Mm-hmm.
There have been studies since that say, actually, we are seeing fiber conversion,
Right.
that you can see an increase in type 1 muscle fibers.
Yeah.
So I think we're more open to that. So I'm not sure this is a nefarious case, even though he was paid by Armstrong's team, of somebody trying to fabricate something to hide doping. I do personally feel open to the possibility that this was just a researcher with some very interesting data who might have made a few mistakes. But you look at his previous research and all the work he's done on efficiency, truly believe that efficiency could improve. And since then, there's been some signs to show, actually fiber type can change.
Right. And maybe there is an easier conversion between a 2A and a 2X fiber. And I think that conversion between a type 2 and a type 1 fiber might be a little bit harder, but I think that we're generally accepting it does happen now. We do have to ask, like I said, are these results still valid in light of the doping throughout the years?
That's the second question. Yeah.
And I think that Dr. Coyle at the time, a researcher that maybe had incomplete information and is just trying to connect the dots. Maybe there was an extra dot in there that needed to be connected, but it was invisible ink, so he couldn't connect that one. You do have to wonder, because of the performance-enhancing drugs, was the training better? Was he able to handle more volume at higher workloads? Did that increase the conversion to type 1 fibers? Did that help push this fiber type change, a little bit faster to a greater degree over the years? I think that we may never know. People do say the effects of doping last much longer than just sort of maybe the transient increases. Once your hemoglobin goes back down, your VO₂max goes back down. It's not as if all is forgotten in some regard, right? You can still be performance improved after that, even though you're off the drugs at that point in time. And maybe a way that you're better is through something like this. Maybe it does push the efficiency a little bit better because we're able to get a little bit more fiber type conversion.
So I'm really glad you brought that up because, like I said, there have been studies since that have shown improvements in efficiency. And some of those studies, including the one that I just mentioned, as I remember, bring up the fact that when you see athletes do hypoxia, go up to altitude, or train in a hypoxic chamber,
or breathe carbon monoxide.
Yeah. That can actually improve efficiency a little bit.
Sure.
And remember, Armstrong was on EPO. Basically, when you put yourself in a hypoxic state, that increases your natural EPO. So you're doing the same thing as what hypoxia would do to you.
Correct.
You're doping at a level higher than what your body would normally produce, but it would produce the same effects. So there actually is now research showing that doping could potentially, there hasn't been the direct study of, yes, here, we gave this person EPO, their efficiency improved.
Yeah.
But we know that hypoxia can affect efficiency. So there is evidence that the doping could have improved his efficiency a little bit.
Right. And so we've brought it up a couple of times. We're talking about hypoxia now. So I just want to bring this full circle. Athletes have been purported. There's been rumors that people are using now carbon monoxide. Previously, it used to be xenon gas. The way that these things work is instead of going to altitude, instead of injecting EPO, you can trick your body into thinking, actually, I guess you're making your body hypoxic by breathing in either xenon or carbon monoxide. And this kills you, right? Because the carbon monoxide binds to hemoglobin and it sticks to the hemoglobin. It doesn't fall off the hemoglobin. And that means oxygen can't get to the hemoglobin, which means you can't get oxygen to your tissue, which means you're hypoxic, which means you do this too much and you die, right? So do not, if you are listening to my words, do not try to do this to improve your performance. The reason that people were using xenon gas is it has a little bit less affinity than carbon monoxide does. Carbon monoxide holds on pretty tight. Xenon holds on kind of tight, but it falls off sooner, which means you're less likely to go fully hypoxic here. But this is a way that people are, because it's undetectable, you can't find EPO in your body when you're breathing in these gases. This is a way that people are trying to dope and increase their hemoglobin mass now. But it seems pretty dangerous.
Yep. No, agreed. So I'm glad you said that. Please don't do it.
Yeah, don't. It's totally not worth it.
Yeah. So where I'm at with this Lance Armstrong's study, and I'm interested in where you're at. Dr. Coyle has done a ton of great work in the exercise physiology world. There is a lot that we now just, it's fundamental when you study exercise physiology that he discovered. And I think he has been a fantastic researcher through the years. So I hate seeing a study like this taint him. I personally want to believe there was nothing nefarious here. I think he would just kind of lucked onto the rider that he got.
Yep.
He got incomplete data in light of the fact that we now know Armstrong was doping.
Yep.
I think that kind of invalidates all the data. So I don't think it was a nefarious attempt to help Armstrong hide his doping. I think you just have to look back on it and say it's just not a great study, and you can't draw any conclusions from it with what we know now.
Yeah, and I don't even think you can't draw conclusions because of anything in regard to Dr. Coyle. It's that we don't know enough to know how the doping affects the things that he measured. This paper could be 100% valid, or it could not be. We literally have no clue, which means that I don't know that we can trust this and cite this or whatever for future work. But again, I think that Dr. Coyle was doing the absolute best that he could at the time with the information that he had. And, recorded some interesting information, was trying to get it out to the general public. And we have another page in that book now that helps us see the bigger picture.
Yeah. I have seen enough research to say there does appear to be some fiber type conversion. It takes a long time.
Yep.
That you can improve efficiency. If people ask me for my evidence, I'm just not going to use this study as one of the pieces of evidence. There's enough other good studies now.
I think that that's probably worthwhile, Trevor. Maybe we should do an episode on fiber type, on plasticity of fibers. I think we've talked about it a little bit when
We've never done a whole episode.
We haven't, but we did kind of like one of our physiology 101s. I think we discussed it a little bit. It could be a mechanism, could be an interesting thing.
I think that would be a really interesting study because even Dr. Coyle mentioned this at the time that there had never been longitudinal studies done.
Correct.
They had done comparisons of elite endurance athletes to amateurs showing, yes, those elite endurance athletes had higher percentages of type 1. But the question was always, were they born with it or did they develop it? And at the time that this study came out, they didn't have an answer.
Yeah, it looks like they did a cross-sectional observational study in 91. Yeah.
Yep.
Okay, interesting.
All right. Do we leave it there? Any last thoughts?
No, man, let's close the chapter in this book. Move the heck on.
All right. Good conversation, Rob.
Thanks, Trevor.
Thank you. That was another episode of Fast Talk. The thoughts and opinions expressed in Fast Talk are those of the individual. Subscribe to Fast Talk wherever you prefer to find your favorite podcast. Be sure to leave us a rating and a review. As always, we love your feedback. Tweet us at @FastTalkLabs. Join the conversation at forums.fasttalklabs.com or learn from our experts at fasttalklabs.com. For Rob Pickles and Dr. Edward Coyle, I'm Trevor Connor. Thanks for listening.